Welcome to the series of lectures on inferential data analysis. There are 3 parts to this lecture, just like always. Now, these are the learning objectives for this unit. I want you to be able to describe what inferential statistics are and what we mean when we say that. I want you to understand the logic behind inferential statistics and the basics of hypothesis testing, what they're talking about, and describe the different types of inferential statistical analyses. Now, don't panic. All of this is going to be conceptual. You're not going to be doing math. You're not going to be doing these analyses. What you need to be able to do is recognize them and know when they're appropriate to use. So we'll get started. First of all, inferential statistics. The purpose of inferential statistics is simply to draw inferences about a population based on an estimate from the sample. So you take a sample from a population and then you run some analyses, and that lets you make some inferences about the population as a whole. In other words, you want to draw accurate conclusions about a population, and so you use this sample to represent it. The actual analyses involved are very specific statistical procedures that accomplish that purpose, that let you make inferences about the population and what's going to be happening. Now, the logic behind all inferential statistics is the probability. The whole idea is that you are stating the probability that the population is like the sample that you analyzed. So it's a very scientific way of giving the degree of our confidence in predicting something. So if I want to know if students' attitudes towards science have an impact on their grades, and so I do a really fun unit that's intended to help them to have a better attitude about science because they enjoy it and it's engaging. What I want to do from my sample is run some analyses and be able to state how confident I am that this applies to the whole population as a whole. I want to talk a minute about probability. Probability is difficult to understand. It seems to be one of those things that people get very mixed up on very easily. But the basics of probability are simply that you're taking the number of possible hits or successes or events, the number of possibilities, and you divide that by the number of possible outcomes you could have. So if I ask the question, what's the probability of rolling a 3 with one die? I'm looking for one hit, just a 3, but the number of possible outcomes are 6. So I'm going to take 1 and divide it by 6. So the probability of rolling a 3 is 1 in 6, or 0.717, or 17%. Now, every time I roll the dice, I have a 1 in 6 chance of rolling a 3. If I roll and I get a 1, and I roll and I get a 4, and I roll and I get a 5, the chances don't change the next time I roll the dice. I still have a 1 in 6 chance of rolling a 3. And that's the part that people seem to get mixed up in or confused in. The previous sampling or the previous rolling of the dice does not affect the next time I roll the dice. Now, we use a range, and this will look a little bit familiar because we've used a range like this before for correlations. We use a range from 0. 0.0 would be the chance I have of rolling a 7 when I roll one die. It's 0. It's not going to happen. All the way to 1, which would be my chance of rolling a number from 1 to 6, anywhere between 1 and 6 with one die. It's going to happen every time. So that's what we mean by a range from 0 to 1. Now, we'll go back to this a little bit. I talked before about the sampling error. It always exists, and what it means is that every sample I draw from a population, even if I draw them randomly, every time I draw a sample from a population, it's going to be slightly different than the actual population by chance, and it's also going to be slightly different from any other sample I could draw from out of that population. And what I mean by different is I'd be looking at the mean and the standard deviation, how spread out that the scores are on whatever I'm measuring from the mean. So remember, if I have 300 students and I draw a random sample of 20, I can measure the mean and the standard deviation for that 20 students, that sample. But then if I draw another random sample of 20, that group's going to be slightly different from the first. And that's why every time we do a statistical analysis, we are going to have sampling error. And we just have to recognize that and acknowledge it. It's never going to be perfect. Now, I'm going to go back and review a little bit on the sampling distribution. What we're talking about with the sampling distribution is if I were to draw an infinite number of samples from out of those 300 kids, if I were to just keep drawing over and over and over again, 20 kids from out of that sample of 300 students, if I did that an infinite number of times, what I'm going to do with their scores is in theory, I'm going to find this normal curve of distribution of their scores. And what we do with a sampling distribution, instead of calling it a standard deviation, they switch the name of it on you, and now it's called a standard error of the mean. And this would be just if theoretically we could draw enough samples. It doesn't exist. But we build all of our probabilities on this normal distribution. In other words, if I run a statistical analysis, I'm saying that the probability, I'm going to say how confident I am that this score is the mean for the population. And then I'm going to give a standard deviation so that you know how spread out that is around the mean. Keep in mind with this normal curve, and I've talked about this before, and there was a good section in your textbook also, that the red arrow, if I could make this infinite number of samples, I would find that 2/3 of all of the scores fit in either between one standard deviation below and one standard deviation above the mean, where that red arrow is. Look how many, remember this is a frequency, look how tall that bell curve is right there. So 2/3 of all the scores are going to fit within a standard deviation one way or the other across the mean. And what's really wonderful for statistical purposes about a normal distribution is that 96% of all the scores, all those frequencies, are going to fit between two standard deviations. So between two standard deviations above and two standard deviations below, 96% of all the scores are going to fall there. So let's take an example. This is not from education, but we'll use height because it's easy to understand. As the bell curve gets taller, that means the frequency of that score is increasing. So you can see right in the middle, the number of people, right, that are normal height, and we're going to call that the mean, that's where most of the people are. They're normal in height. Now, if I go out one standard deviation either way, to the left, I'm starting to get to the short people. And if I go one standard deviation above and moving on to two standard deviations, that's the tall people. So between the two standard deviations below and the two standard deviations above, 96% of the population, their height fits right within that part. Now, in the world though, we have some very, very, very short people. And at the other end of the spectrum, we have some very, very, very tall people. But those are so unusual. And look where they fit when you get out 3 standard deviations from the mean. Look at how few of them there are in the normal curve. So that's what we're talking about with a normal distribution or a normal curve. Now going back to inferential statistics then. Inferential statistics is the probability of the population mean being within a specific range of values based on the sample. And that's what we call the confidence interval. Sometimes you will see that the mean is a certain amount and they will give you a probability. But sometimes you will see written that they've got a confidence interval, which is the range in which the population mean is. So we know the probability of the general population when we use inferential statistics. We know the probability of the sample mean. And what we say then, this part in red is really, really important. What we're saying when we run our analyses is that the intervention changed that sample, or it happened just by chance. And that is the whole concept behind inferential statistics. Did it happen because of the intervention, or did it happen by chance?